We have been looking at applying binary search to very interesting problems. Specifically, we looked at three problems: the flight path problem, where we had to find the first value that went over a threshold; then the peak search problem, where we had to find the peak value, the index of the peak value in a non-sorted data; and then we looked at the shipping capacity problem, where we had to find the minimum shipping capacity, that allows us to, let's say, ship those items in a given number of days. Now, this is something very interesting. These problems did not look like search problems to start with. And hence, I would like to end this, let's say, set of videos with this very interesting observations that I've read in a book. This book is by, Daniel Zingaro, chapter 6 of this book called Algorithmic Thinking. Now, what I found really amazing about this is that there is a separate chapter dedicated to binary search, and that's this chapter 6. We often read binary search as a method for, let's say, finding items in a sorted list. That's exactly where we started, and that's where the whole discussion starts. But as we have seen, the application is much beyond. In fact, the chapter 6 here, makes two observations, which I thought I'll summarize and, sort of mention here. Basically, it says that, look, if there are two key ingredients in a problem, then binary search is a really good method. So first one says is hard optimality, but easy feasibility. So what this the statement is, basically, for some problems, it's hard to come up with the way to find an optimal solution. Fortunately, in many of these cases, it's considerably easier to determine whether or not a proposed solution is feasible. In fact, we saw this very, very vividly in our shipping capacity problem. Very hard to figure out what is optimal just by looking at the numbers. But when we turn the problem around, we realize that, okay, for a given shipping capacity, I can find out, can I answer, or can I, let's say, transport, this material in this many days, which means we can determine if a particular shipping capacity is feasible or, let's say, no, not feasible. And that is much easier than immediately figuring out what is optimal. So this is ingredient number one. We saw this vividly in, let's say, shipping capacity. Ingredient number two, basically kind of sortedness or monotonicity, but said in a very different way, but very useful way. In fact, I would say infeasible feasible split. So what does this mean? Basically, we need the problem to exhibit the property that there is a border between feasible and infeasible solutions. All solutions on one side of the border are infeasible. All solutions on the other side of the border are feasible. You recall when we looked at all the three problems, I kept highlighting this fact of behind and ahead. Let's just look at it once again. For example, in the very first problem, altitude versus index, we knew at every index whether the threshold crossing is ahead of me or behind me. So notice this is the sort of feasible infeasible split that, do I have to move in this direction or do I have to move in this direction? At every point, I know that. Likewise, in the peak search problem, we always, at every index, we have an idea whether the peak is ahead of us or behind us. And similarly, in the shipping capacity problem, there is an infeasible zone, there is a feasible zone. We know that the optimal solution that we're looking for is, let's say, ahead, as basically the border of these infeasible feasible zone. So this is a very, very interesting way to look at it. Basically, this is like saying that, look, there is a kind of monotonicity in this whole data. There's sortedness in this data going from here to here. Something cannot be done, something can be done. As I increase the size of the ship, things become from feasible, let's say, infeasible to feasible. And that, like I said, is a nice way to look at it. I think both of these are very insightful observations, very nicely put, because it kind of highlight how binary search is really applicable to a wide range of problems. But needless to say that in order to understand that these components are at play in a given problem, it takes practice, first of all, to understand these principles, and then to sort of internalize them so that we can recognize these patterns in a problem and apply binary search. There is really no substitute to practice when it comes to programming. But I hope that our detailed discussion and detailed treatment of binary search, the three example problems that we solved through these videos, and the many practice problems that exist out there will give students the confidence to take on these problems in a meaningful manner. Very, very happy to discuss these, to share your thought process, to understand how people are approaching these problems. Do reach out, do leave comments, and do share examples where you think binary search could be used. Binary search is clearly powerful, clearly useful. Mastering it can make you go a long way. Do look at our website www.ybyte.in, because at Ybyte we learn programming, we learn algorithms in a fun way, which is rigorous yet systematic, because we want everybody to enjoy coding. Take care. Thank you so much. Bye bye.